building a story for A-level students and or other students, it is important to get them to know what you're talking about. So, the first thing we're going to do is we're going to make... this isn't my famous don't give them the title thing, don't give them the complicated word. There are several complicated words today. This is us building a stay bridge. Yes, one of those. Okay, and the question is, what type of material should we use for our stay bridge? Yes. Particularly, not for these, the tension wires, but for the surface of the bridge. So perhaps we should even change our bridge to make it slightly simpler, so we're just concentrating on the properties of this material. So what are we going to use? Well, I'll ask my students, and they'll come up with things like gold, plastic. You get a lot of different answers. Hopefully sooner or later somebody will say steel. And I'm going to say, yes, let's use steel. Somebody else might say, oh, but concrete is also used for bridges and is cheaper. I'm going to say, yes, it is, but it has a problem right here in the middle. And that's the reason why, if you're going to use concrete or a ceramic, you're best off with a curved structure, and therefore there's no tension at this point trying to break it apart, because bricks, stones, and concrete are no good in tension, so you need this kind of shape in order to have everything in compression, or there's no sort of pulling apart. Let's have a look at this bit a bit better. So if we're going to load this up with a truck full of gravel for a road somewhere, let's give it another wheel. Okay. Then what that's going to do is going to give us a lot of bendy force down here, and this bit is going to split apart. And one of the things that concrete's no good at doing is being split apart. It breaks. Concrete is really strong when you compress it. You can put lots and lots of weight onto our structure if we just use compression. That one's great. That one's a failure. Bridge breakage. So let's use steel. Great. And there's lots of different types of steel. We can add lots and lots of things like nickel and chromium to change the properties of the steel. There's always add carbon. You definitely always add carbon. If you don't add carbon, you've got iron. And unfortunately, my favourite superhero is Iron Man, but Iron Man would be soft and pliable, because 100% iron is soft, bendable, and pliable. So Iron Man, unfortunately, no good. So you add carbon to get the Man of Steel. And then if your students know the Man of Steel, if they really know their superheroes, they know that's Superman. Okay, and Superman would be definitely much better than Iron Man. Iron being not good, Steel being nice and good. So what are the properties that we need? So we need it to be good in compression, good in tension. Okay. I mean, tension is very important for these wires up here. They're going to be in tension at all the time. This bit here is going to be in compression all the time. On here we've got tension at the bottom and compression at the top, as the whole bridge tries to go from this shape to this shape because of the truck. Yeah, tension pulling apart the atoms here, compression squashing together these two atoms there. Cool. Hopefully that will work. The students will feel it. If not, possibly a good idea is to get one student's hand and to bend it like this, and maybe, or just the finger, and he'll feel here it's being pulled apart, and here it's being pushed together. Anyway, it's always good for a laugh to have a student out and have their hands tortured. Well, not totally tortured, of course. Okay, here we go. Right, so we need to know other materials and things. So what else do we need? Oh, we need it to be strong. Oh, I've got the R. Strong. Yes, strong things won't break. So, yes, you need it to sustain lots of force of tension and compression. So, strong in tension, strong in compression. Any other ones? Well, okay, someone might say hard. That means it doesn't scratch, so we're going to make this bridge out of diamonds. No, not really. You want it to be quite hard, but that's not really the one. What we want is no bendiness. So what else are we going to have? Tough. Well, that means it can. Welcome back. Sorry, we had a run out of battery problem and run out of space. So, force we need. So it's not fair to compare these two wires and put force on both of them. You can't compare them. So there's another thing apart from force that matters. Yes, it is. It's the cross-sectional area again. So, what are we going to do with force and area? Well, obviously this one should be able to take more force than this one. And in order to make these two cylinders equal in the thing over here, we need lots of force and very little area. Force divided by area. Lots of force, very little area should get me my, well, what am I going to call this? Okay, well then we're going to get breakiness from students. Absolutely, my breakiness. Yes. So, this is my ability for it to change shape. So I'm going to get rid of breakiness and get in changey shapiness. Yeah, okay, at this point we're going to get the spelling going all over the place. Let's see if my camera can see that one. Good. Changey shapiness. That will have to do us. Right, okay. And changey shapiness, yeah, obviously, more force, less area, you can bend it into a different shape. The changey shapiness. So force over area. F over A equals, well, that's called the stress. The stress, the forciness. Yeah, okay, good. I might be regretting using changey shapiness and need it later, but we'll get to it. The stress, force over area. The how much force, let's just there's a forciness. Let's put an E in there. The forciness. Yeah, so that's much better because I'm going to need that one later. Yes, the forciness. Force over area. Lots of force, very little area. You're going to stress the metal out. Out. Oh, that's good. Doing things on the hop as we go. Never having a plan. Well, not as such. So the next thing we need is the, okay, so this is going to become this. Okay, if that becomes that, well, it won't. It's going to keep the same volume. So what you actually get is it thinning out in the middle. So in Sheffield, the bars that we used for that shape to start with. We put them in the big machine and they got very thin in the middle until eventually they broke. Okay, I guess the idea. So here, it's got longer. Yes. What are we going to call it if it gets longer? The longeriness. Okay, here we go. Yes, students come up with longeriness. Now, even if a student did say extension, I'm going to have longeriness in there, because longeriness is more intuitive, whereas extension is the word that we use. Okay, so is it fair to test something that starts off as that length, its extension, and another one that starts off with that length, its extension? No. Obviously, if it's twice as long, the extension will be twice as much. So therefore, we get extension and original length. This is the original length, and it's going to get longer. It gets twice as long, twice as long. Right, okay. Right, what are we going to do with extension and original length? Are we going to add them? No, obviously not, Mr. Stevens. Multiply them. That means that this one will definitely win, because it's this original length times that amount of extension. No, they're both made out of the same material. They will both get 20% longer. So what are we going to do with extension and original length? Yes, it's a divide. Extension divided by original length. Okay, and we need a word for this one, the longeriness. Yeah, that will do. The longeriness. And then, of course, once you've got an intuitive word from the students, you put in, it's called the strain. Yes. That's something you do with peas, Mr. Stevens. Yes, the same word is used for peas. But what I mean, longeriness is the strain. Now, we've got the stress it out and the strain. So, our final thing is we want the good for bridges measurement. Equals, well, do we want lots of strain or not very much strain? Hopefully, when we do a vote in the class, it's good to do votes sometimes, blindfolded votes, or even better, nose on the table votes, so therefore people can't look around and just go with whoever. Nose on the table, put your hand up, or don't put your hand up. Put your hand up if you think strain goes on the top, and then everyone sits up and laughs. That's fun, strain. There shouldn't be just a matter of listening. There should be interaction with the students doing things, coming to the front of the class to watch demonstrations, walking around the class, doing experiments. Try to do one experiment every lesson, even if it's just a small experiment like getting a balloon and trying not to pop it when you stab a pin into it. It can be done. It's in my videos. Yeah, a whole load of like 5-minute videos. Do those at the end of the lesson, particularly if the students have, worked hard and concentrated. No one's messed about. And if someone does mess about, then, no one gets the experiment, and that makes all the students think, just stop messing about so we can do the experiment because they're fun and they get balloons out. And setting light to tea bags to make them fly up, convection currents and all that. They're brilliant. All of these things A-level students should enjoy as well. So the experiment, even though it's a short experiment, at the end of the lesson is the prize for everybody working hard, for the whole team working together. Right, okay, where are we back at? Right, do we want the bridge to be able to take lots of force? Yes, we do. Do we want it to take lots of force even if it's a small area? Yes, we do, because we don't want to be making the bridge out of things that are big. We would like it to just be things that are smaller area. Smaller area means we spend a lot less money on materials. And the bridge is much cheaper, comes in price, and that means we get to build the bridge, not the other people who said the bridge was going to be more expensive because they picked the wrong steel. If you pick the right steel, you need less of it, and it weighs less, and everything's brilliant. You want a bridge that doesn't weigh very much, because as soon as you make a bridge that's very big area for all the struts and stays and stuff, you end up with these concrete compression towers having to be even stronger if all the metal is heavier. So, yeah, we do want a bridge to be lightweight. Hence modern bridges. Unless, of course, we happen to be the Romans, who built a bridge like this, with the keystone going on last. They put loads of wood to hold it all up until the keystone was put under, and the first thing that happened was the architect had to stand underneath while they took all the wood scaffolding away. There's a couple of guys that got crushed that way, but they made good bridges because nobody wanted to get crushed. No cheaping out in the Roman world. That's the way things should be. We've had a couple of buildings fall down in the last decade or so in China and other Asian countries, and a couple burned down in the UK. Not good. Somebody's fault. They should have been forced to live there. And then they'd make it better. Okay, right. So we want it to be able to cope with lots of stress and make very little strain. So where are we going to put those stress? Goes on the top, yes. And so what are we going to... Mr. Young... He's a hero. He's a hero because he did exactly what I would have done. I would have named it after myself. This would be Mr. Stevensness. But no, it was Mr. Young. And so he named it after himself, and he called it Young's thing. And it's called Young's Modulus. Yes. Young's amount of goodness for steel. Young's Modulus is stress over strain. Stress is force over area. You want it to take a very large force and a very small area. Because, very small area. Otherwise you have to spend 10 times the amount of money on steel. Don't use iron. Use steel with a little bit of carbon in it. And, for bridges, it's just iron and carbon. You don't use the sort of steels that you might need in Formula 1 engine. And strain is extension over original length. And the good thing about all of these equations is now you're doing A-level, they're all in the formula booklet. So what's the title for the lesson? Yes, it is. Okay. And at this point, we get a student to come up, and without looking at the rest of the board, to just write the title. And and everybody, if he gets it right, writes it down. Excellent. There you go. How to teach Young's Modulus. Get the words in last. Do an experiment, because everybody's worked hard. They've all written their notes. Do an experiment, and everyone's happy. Boom! Boom.